For 40 years, performance scaling was simple: clock transistors faster. That era is definitively over. The ledger that treated the transistor as a zero-cost resource is now closed. The future of compute is no longer about monolithic speed, but about architectural transformation. The primary constraint is not transistor density, it's heat. We are suffocating under the weight of power density. Dennard scaling, the principle that allowed power consumption to drop as size shrank, died years ago. We can cram more logic onto the die, but if we turn it all on simultaneously, the silicon substrate simply melts. This is a fundamental physics problem. To execute 40-year-old x86 code as fast as possible, modern cores use massive, speculative, out-of-order execution. This engine constantly guesses the future, allowing for spectacular single-threaded performance. But the complexity required to maintain coherence and rollback state, the reorder buffer, is immense. That complexity is costly, both in terms of power and in creating security vulnerabilities like Spectre. The alternative championed by ARM and other RISC architectures is superior power efficiency. They accept a trade-off: higher instruction counts, but simpler in-order pipelines. This requires less complex hardware for state management, which means designers can pack far more functional cores onto a fixed thermal budget. This trade-off is why ARM dominates mobile and increasingly the data center. The true performance bottleneck isn't the CPU core frequency, it's the latency of moving data. This is the memory wall. Every cycle spent waiting for data to travel from DRAM means a register is idle, wasting massive power. The solution is no longer about faster clock speeds, but about brute force minimization of physical distance. We must move from a 2D PCB world to 3D architecture. By using through-silicon vias, or TSVs, we stack memory directly on the logic die. This massively reduces wire length, leading to lower power and orders of magnitude higher bandwidth. Access time drops dramatically. The critical constraint here, however, is thermal management. Wicking heat away through the entire stack limits the maximum operating frequency of the logic layer. For certain workloads, we eliminate the back-and-forth data movement entirely. Neuromorphic systems perform the calculation where the data sits, using the memory cell itself to do the arithmetic. This is an accelerator, not a general-purpose CPU. It excels at sparse, event-driven tasks like sensory processing, but completely fails at tasks requiring complex branching logic or high-precision floating-point calculations. Silicon is reaching its physical limits, especially due to high leakage current as transistors shrink further. The industry is hunting for new materials like graphene and carbon nanotubes, which offer superior electron mobility and less leakage. The challenge here is manufacturing maturity. We have 6 decades of refined silicon lithography, but the consistency and reliability needed for mass-produced CNT-based chips are simply not there yet. The ISA landscape is shifting dramatically towards specialization, enabled by RISC-V. As an open-source instruction set, engineers can customize the architecture itself, adding bespoke instructions that map perfectly to their specific workload, whether it's machine learning or cryptographic hashing. This freedom is powerful, but it guarantees fragmentation, and the software ecosystem is the critical constraint holding back its full mainstream adoption. We are moving into an era of relentless heterogeneity, where the traditional general-purpose CPU is just one component on the die. It is becoming the central nervous system, coordinating an army of specialized silicon accelerators, each optimized for a tiny subset of tasks. The key challenges ahead are not theoretical speed, but pragmatic constraints. First, thermal dissipation, extracting heat fast enough, driving us toward integrated liquid cooling. Second, toolchain inertia. The software stack must evolve to seamlessly schedule workloads across x86, ARM, RISC-V, and accelerators. And finally, the memory compute gap. We must continue migrating memory onto the logic die to make every data access resemble a register hit.